All right. Hello. Welcome back. It's 1.2. It's an exciting time. What are we doing here? We are displaying quantitative data. That is data that has a numerical measure, right? Or it might be a count, because a count isn't a measurement. There is infinite precision to a count, whether it's a finite level of precision with a measurement. You remember that from like science classes in the first week. Every science class you've ever taken, right? Yes, I hope. Okay. We got something called a dot plot, and it's hard to want to talk a lot to you about the dot plot because this is a sticker chart. You have seen a dot plot before. This is your kindergarten sticker chart. How many times did little Jimmy do some mundane activity during the day? And you put a dot for each occurrence. I don't know how to spell that. Let's put a dot. What does this say? This said 1 happened once. 6 happened 1, 2, 3, 4, 5, 6, 7 times. Why is this not nice? Because anybody can interpret one of these, I think. Why do I show you this? All right, so this could be, the number of students who completed homework in, my third, fourth block, whatever. And I put a sticker every day for how many students completed the homework, and the most common answer was 6. Great. So what's the big point of today's lecture? It's not very long. What's the big point? The big point is describing the overall pattern of a distribution. If you're asked to describe a pattern of a distribution, I'm going to ask you to remember your socks. And I do this in kind of an opposite order. Shape. Does it show symmetry or skew? Where is the center? For center, I'm going to use this word typical. What's a good measure of what is typical? Outliers, unusual data points that stand out, and spread. What is the range? What is this thing called the IQR or the standard deviation? We'll talk about those. So we're going to mention shape, outliers, center, and spread. I butchered the order that I placed those in, but you're going to talk about those. Socks, costs. You can rearrange the letters to your liking. So now we got to talk about what these things are. The first thing we're going to talk about there is shape, describing the shape of a distribution. 3 very common shapes we might describe: one that's symmetric, skewed left, or skewed right. Symmetric. Take a moment, consider what's a characteristic of human life that might be symmetrically distributed, and a lot of physical characteristics are actually going to be symmetrically distributed. So maybe this could be something like, I can spell, height, where there's a most common value in the middle and the extreme heights to one side, or who's the tallest person in the building? I don't know. Mr. Jones and Miss Chan on either end of the thing. You don't get that much taller, that much shorter, and the farther you get in one direction or the other, it's about equally likely to happen as far away in either direction. Note about the mean and the median. Here, the mean is equal to the median. They are equal. So this could be something like height, weight, I don't know. And a skewed left distribution. It says the mean is less than the median. So here I might notice that the mean and the median are in the same place. I can use 2 different colors for that even. Use blue for the median. Oops. Red for the mean. What do we notice here? So what's skewed left? What's a distribution that might be skewed left? And one that comes to mind for me might be something like I don't know, life expectancy. or lifespan, right? How long do you live, right? And there's, we don't have that many people dying in their 30s, right? Not that many people die in their 30s. Where do you die? You die in when you're old. So what do we see here? Mean is less than the median. Well, the mean might be here, whereas the median might be over something like here. What does that mean in terms of the mean and the median and the skew? Well, I'm going to make a little note down here. The mean follows the skew. When I say follows, I mean, well, it's heavily influenced. That is, it is not resistant to extremes. The mean follows the skew. It's heavily influenced by it. It's not resistant to extremes. And I think the next example might be better on that. Skewed right distributions where the mean is greater than the median. Again, mean in red, median in blue. What could this be? This could be income. This is, how much money you're taking home every year. And I posit to you, all right, which one, what happens to the average income when Patrick Mahomes walks in a room? What happens to that? And what happens to the median income? Think about the difference between those two. What happens to the mean and the median income of the room when Patrick Mahomes walks in the room? Well, the median doesn't change much. Think about how the median's calculated. Put everybody in order. You got 100 people in the room, 50 and 51, median's somewhere in there. And then Pat Mahomes walks in the room. Well, there's 101 people in the room. The median didn't change much. The mean changed a lot. So I say out here, the mean might be out there. Think of Mahomes. I'm going to put little Mahomes out here, and he's making $50 million a year, whatever he's making, and I'm down here making 1/1000th as much. This is clearly a log scale. So what's my big point? The mean follows the skew. It's heavily resistant by those extreme values. If you want to write it down, what happens to the mean and median when Patrick Mahomes walks in the room? What happens to mean and median income when Mahomes enters a room? And I'll say it again for you. I don't have room to write it down. The median income doesn't really change. Think about that. Just shifts over one in the list. But the mean, you've all of a sudden added 50 million to the numerator and 1 to the denominator. It's going to go up. So example down below, how do the annual energy costs in dollars compare for refrigerators with top freezers and refrigerators with bottom freezers? So what do I need to do here? I need to describe the shape, the outliers, the center, and the spread of these. So I'm gonna do an example for you. We're just gonna describe a SOX. So let's do it. One thing I forgot to mention, back up here. When you're describing this, you need something more. Plus context. Everything we do requires context. What's context going to be? Name the variable. Use the words. Talk about the situation. Give the numbers a label. Don't just have naked numbers flying around. So, how do the annual energy costs in dollars compare refrigerators with top freezers and refrigerators with bottom freezers? Great. Okay, so I'm going to use like green for the top and, use a different color. Red for the bottom or something, maroon, whatever color that is. How do they compare? Well, I need to talk about their shapes, their outliers, their centers, and their spreads. And so let's talk first about maybe the shapes of these. The shape of both distributions is, well, what? up here looks pretty symmetrical. Think about if here's the middle, looks about the same on either side. If you want to talk about this one, I don't know, is that one symmetrical? Maybe this one's a little bit skewed right? I don't know. The shape of both distributions is, let's say, fairly symmetrical. But let's talk about what we might see on the bottom. With bottom freezers having some right skew, some potential. The shapes of both distributions is fairly symmetrical with the bottom freezers. Maybe the bottom freezer's a little bit of right skew. Maybe it's a little bit skewed to the right, but it's not like terrible, but it, some potential right skew. All right, so we've talked about the shape. Let's talk about the center next. Let's go ahead, I'll switch colors. Looks like top, I don't know, like 55. Bottom, I don't know, like 70. What am I drawing a line at? It looks about like the median. The median energy cost, that's context right there. That's all you need to say. The median energy, not the median energy cost. What are we talking about? Name the thing. The median energy cost for top freezers is, I don't know, what is that, 55 we said? Well, for the bottom, it's 70 per year. Cool. And what do we say something at the end here about, I'll switch to orange. Shape center, spread. For now, we're just going to go with the range. We're just going to go with the min, max, max minus min. What is that, like 65 minus, I don't know, like 45. Top freezers have a range of, what do we say, $20, while bottom have a range. And now we can kind of bundle outliers and range together. I see I'm going from like, what is this, like 47 right there. This is like 107. So we could say with a range of 60, and I'm going to talk about this guy kind of bundled in with the spread, excluding a potential outlier at 142. You're gonna, what I just did there, that mess, talking about shape, center, spread, and outliers, you're gonna have to do that all the time. And that's a real life skill, saying, okay, that's the distribution of test scores, that's the distribution of car price, that's the distribution of something that you're in charge of, that you got to talk about maybe. Okay, so shape, center, spread, outliers. You have some choice right now as to what measure is better or easier to calculate. We'll talk more about that later. I will a note on the mean and median. One more thing I'm going to add. We're going to use the mean when it's symmetrical. We're going to try and use the median when it's skewed, and I'll come back to that, I believe, at the end of the notes. So definitely pause, take a look at that, because we're going to do that all the time. So moving on, again, a very short section of notes. I have one. I'm done very quickly here. Okay, so stem plots, stem and leaf plots. You will have stem plots. You have probably seen them on the ACT. I don't see them in the wild very often because they're kind of stupid. But we will look at these nonetheless. What do I see here? Stems and leaves. You know, and you can repeat leaves. So you have always gonna have a key here. What is this nice for? This is nice for, I don't know what this is nice for. I think it's kind of stupid. I will do this for you just to kind of see something. Notice that you can kind of visually do this. Rotate. We're going to go 90 degrees. What is that, counterclockwise? And we get something that looks so you can rotate and you can see, you can kind of, yeah, look at that. You can see the shape if you kind of turn it in your mind. So stem and leaf plots are silly, I think. You do need a key to say this. The stem is the first number, the leaves are the last number. First, last. Key thing you need to do here is make sure you don't skip empty stems. So notice we didn't have a measurement in the 600s. That doesn't mean we skip the 6 level. Big thing there that AP loves to ask you questions about. Might be something like skipping an empty stem. Right. Okay. So take a look down below. Compare the two distributions of phone battery comparisons of brand A versus brand B. And this one is kind of goofy. I want you to do it, but a few things I want you to specifically note. This key, I don't think is sufficient. I also want to see something like, well, I think that key is wrong, in fact. I'd want to see the key maybe like 5, 6, that means 56. But also I want a key, what the heck does this one mean? The 6 in the middle is the stem with the 1 on the outside? That really means 61. So I'd want to see kind of keys about what it looks like on both sides, because this is what we call a back-to-back stem plot. Why do we do this? To confuse you. I hate these plots. I think they're dumb. But if you're going to do them, you need to understand what the key means. And so the stem is the first number, and even if the leaf's on the left, it's still the second number. So those are goofy plots there. Take a moment, describe shape. Remember, skewed to the right is skewed to big numbers. So brand B is going to be skewed right. Sometimes people talk about right skew as a positive skew towards the positive side. Well, I might see that over here in brand A, that might be symmetrical. You need to put this all in a sentence. Do not bullet list this thing. Sentences. What are we talking about? Hours of battery life. So you need to talk about, okay, maybe symmetrical versus skewed right. You need to talk about where's the median. We got a median maybe here, I don't know, 19, maybe 21. Where's your median? Over here, median, I don't know, maybe a little higher, like 22, 26, somewhere in there. Spread, you can take the range. I see some potential outliers on both sides. You need to put it together in a sentence. I'm not going to take the time to do that there. The last type of graph you might see is something called a histogram. Histogram is for quantitative data, whereas the bar graph that we did last time is for qualitative data. The big difference is the histogram has no spaces between the bars. That's because it's on the number line, There's some pickiness about histograms that I'm never going to test you over, and AP's never going to test you over. There's some like border cases that you'll ask me about, but don't worry about too much. Last thing is a histogram for your example. Records are kept by each state in the U.S. On the number of pupils enrolled in public schools and the number of teachers employed in public schools for each year. Okay, and what do we do with that? We come up with something called a pupil-teacher ratio. right? How many pupils are there for every teacher in the building? And so 2011B number 1, write a few sentences comparing the distributions of pupil-teacher ratios for the two groups, West and East, during the 01-02 school year. So you got some schools on either side, 24 states West, 26 states East. I'll write n equals 24, n equals 26 over here. What's the easiest measure of center to talk about? I might have skipped that in the notes earlier. Think about that. We didn't talk really about center. I mentioned something about mean and median, but there's a third one. There's mean, there's median. What's that last one? Mode. Which one occurs the most often? Yes, okay, that's often the easiest one to spot. Why is the mode the easiest to spot? Because it's the tall bar. All right, so write a few sentences comparing the distributions of pupil-teacher ratios for the states and the two groups during the 01-02 school year. A few sentences, great. Shape, outlier, center, spread. What do you see here? The shape of PT ratios in the West is what? Looks skewed right to me. While it looks pretty symmetric in the East. Cool. What else do we see? The center, shape, outliers. We're gonna skip outliers. We're gonna hold that to the end. The center of the West is I don't know. What is this bin? That's the 14 to 15 people bin. Whoop, not 51, but 15. What's this bin right here? This is the 15 to 16 bin. The center of the West is 14 to 15, while in the East, it's higher at 15 to 16 pupils per student, or teacher. Shape, center, spread. I would just talk about the range. It's easiest to see. The range in the West is 12 to 22, is 22 minus 12 equals 10 students per teacher. While in the East, it's, what is that, like 19 minus 12 equals 7. Shape, center, spread. Are there any outliers? I don't think there's any obvious outliers. There are no obvious outliers in the distributions. Cool. Dying. All right, so shape, center, spread, outliers. That's it. You're doing that over and over. If you had to move, what's an advantage of being in the West? What's an advantage of being in the East? Things to consider. What is an advantage of being in the West? Get a, I don't know, potentially lower class sizes. There's more classes that are, 12, 13, 14, it looks like. What's the advantage of being in the East? Not going to be in a class size of 22. So the East looks a little, you're probably going to be in a little bit bigger of a class, but you're not going to be in a really big class. So you got to consider what's disadvantages, disadvantages. I got a few questions in on essential questions. 1.3 is a big unit. We'll do that next time. Bye-bye.